We're doing something a little different today for this deep dive.
Yeah, we're going way back.
Way back. Because usually when we look back at history, we tend to stop at, I don't know, the Romans, maybe the pyramids.
Right, the human stuff.
Exactly. Or, if we're feeling particularly adventurous, we might jump back to the dinosaurs.
Which people think of as the ultimate ancient history.
Right. But today, we're looking at a stack of research that I can only really describe as the foundation of everything. And I mean everything.
It really puts things in perspective, doesn't it? We're looking at the Paleozoic era.
Which makes the dinosaur era look like breaking news.
It does. I mean, we were talking about a span of roughly 289 million years.
Wow.
Yeah, from 541 million to 252 million years ago. And the source material we have today, specifically this comprehensive report titled The Paleozoic Earth, an integrated synthesis of biotic, geodynamic, and atmospheric evolution. It makes a very strong claim.
Right.
It argues that this isn't just, ancient history. This is the operating system update that made Earth, Earth.
That is a massive claim. But when you look at the data, it holds up. Because when we start this story at the very beginning of the Paleozoic, the planet is completely unrecognizable.
Completely. I mean, if I put you in a time machine and dropped you at the start of the Cambrian period,
right,
roughly 541 million years ago, you wouldn't just be confused, you'd probably be dead in minutes.
Because of the air.
Like suffocated.
Suffocated, yeah. The air isn't breathable yet.
Wow.
And the continents are in all the wrong places. There is zero life on land, no trees, no grass, just bare, windswept rock.
It's rock.
It's rock.
Yeah.
And the ocean. The ocean is filled with things that look like they belong in a fever dream. So the mission of this deep dive is to track how that totally alien world turned into the biosphere we live in now.
It's the biographical blueprint of modern Earth. But before we get into the giant bugs and the shifting continents, I want to ground this for the listener.
Sure.
Why does this specific 289 million year chunk of time matter to someone, driving to work right now? Well, practically speaking, if you're driving a gas-powered car right now, you are literally burning the Paleozoic.
That's wild to think about.
It is. The vast majority of the fossil fuels we use today, coal, oil, natural gas, they were laid down during this exact era.
So we're fueling our modern lives with the ghosts of this specific epoch.
Exactly. But it's more personal than just fuel.
How so?
The Paleozoic established the body plans for almost all modern animals. The reason you have a spine, a jaw, 4 limbs, fingers, toes.
That all comes from here.
Yeah, that architectural blueprint was drawn up right here in the Paleozoic.
So literally when I look in the mirror, I'm seeing a Paleozoic design.
You are. And third, and perhaps most urgently, this report highlights that the Paleozoic provides a mirror for understanding modern climate change.
Because of how it ends.
Right. It ends with the most catastrophic extinction event in history, driven by rapid warming and ocean acidification.
Which sounds very familiar.
Exactly. Understanding what happened then gives us the only real-world data we have on what happens when the climate goes entirely off the rails.
Okay, let's unpack this.
Yeah.
We have to set the stage. And literally, the stage itself was moving.
Yeah, the report calls this the geodynamic stage.
Right, because we aren't just talking about animals migrating around. The ground beneath them was sprinting.
Well, sprinting is relative in geology.
Fair enough.
But yes, compared to today, things were incredibly active. We start in the Cambrian period. This is right after a supercontinent called Pangea had broken apart.
Now, we always hear about Pangea, but Pangea was like the prequel.
It was the prequel. Pangea comes much later. And Pangea's breakup set the scene. But the most important factor at the start isn't just the land moving apart.
It's the water.
Yes, what the water did. The report emphasizes something called the Salk transgression.
It sounds like a very bureaucratic treaty, or maybe a sci-fi novel.
It really does. But transgression in geology is just a fancy word for sea level rise. Global sea levels rose dramatically. And because the continents had just broken up and were relatively low-lying, these rising oceans didn't just, hit the beaches.
They kept going?
They flooded the actual interiors of the continents.
So imagine the ocean rising so high that it spills over the passive edges and just covers the middle of the landmass?
Exactly. Imagine the central United States or large parts of Europe covered in shallow, sunlit, warm water. Maybe 100 meters deep.
Like a continent-sized hot tub.
That is a perfect analogy. These are called epicontinental seas. And this matters because deep ocean's the abyss. They're cold, they're dark, and they're generally nutrient poor.
Right. Not a lot going on down there.
But these shallow seas, they were bathed in sunlight, they were warm, they were the absolute perfect incubator.
So the geography essentially created the laboratory for life.
Precisely. If you don't have those shallow seas, you probably don't get the explosion of biodiversity we see later. But while the water is rising, the continents are dancing.
So who are the big players in this dance? I know we have the heavyweight champion, Gondwana.
Gondwana is the anchor. It's this massive supercluster of crust containing what is now Africa, South America, Australia, Antarctica, and India.
That's huge.
It's massive. And it was sitting mostly in the south, extending from the tropics all the way down to the South Pole.
So that's the stable block. But we have some wanderers too, right?
We do. We have Laurentia, which is essentially the ancient core of North America.
Okay.
We have Baltica, which is northern Europe. And we have Siberia. These were separate continents just drifting on their own.
And they were on a road trip.
A very slow, inexorable road trip. During the early Paleozoic, Siberia and Baltica were moving from cool southern latitudes toward the equator.
They were chasing the warmth.
They were, and Laurentia was already sitting pretty close to the equator.
But as we know with plate tectonics, when continents move, they eventually run out of room.
Right.
They crash.
Inevitably. This continental choreography drives everything. It builds mountains, it changes ocean currents, and it totally alters the climate.
And the report points out one of the most significant dramas in the early Paleozoic involves an ocean that doesn't even exist anymore.
The Iapetus Ocean.
The Iapetus. This is described as the precursor to the Atlantic, right?
Yeah, roughly speaking, yes. It sat between Laurentia, North America, and those other drifting continents. Now, imagine the east coast of North America today, New York, Virginia, up to Newfoundland.
Okay.
It's what we call a passive margin.
Meaning nice beaches, no volcanoes, no earthquakes.
Exactly. It's just accumulating sand and limestone. That's what it was like in the early Cambrian. A quiet, tropical paradise. But by the Middle Ordovician, the dance changed. The ocean began to close.
Subduction zones form.
Yes.
And subduction means violence in geology. That's one plate diving under another plate.
It turns that peaceful, passive shoreline into a violent collision zone. This is known as the tectonic orogeny, a massive volcanic island arc. Think of something like the Japanese islands or the Philippines. That whole arc slammed into the east coast of North America.
So imagine Japan crashing into New York City.
That is exactly the scale we're talking about. It created a mountain range that rivaled the Alps or even the Himalayas, stretching from New York all the way up into Newfoundland.
That's incredible. And the report mentions we can actually still see the evidence of this today.
We definitely can. The report talks about clastic wedges. Basically, as those massive mountains eroded over millions of years, they shed huge amounts of sediment into the basin behind them.
Oh, wow.
So if you drive through parts of New York or Pennsylvania today, and you see those thick layers of sedimentary rock cut by the highway, you are looking at the eroded remains of the tectonic mountains.
That is wild. We're literally driving through the rubble of a collision that closed an ancient ocean.
It connects the deep past directly to the landscape we see right out our windows.
It really does. So while the land is crunching together and building these massive mountains, the air above it is undergoing its own revolution. Let's look at section 2 of the report, the atmosphere.
Yes, this is fascinating.
This is actually one of my favorite parts of the report because it challenges the assumption that air is just air.
Right. We take it for granted.
We think it's static. 21% oxygen, trace CO2. Always has been, always will be.
And the Paleozoic says absolutely not. When we start in the Cambrian, oxygen levels were surprisingly low. The models suggest maybe 5 to 10%.
5 to 10%. If I dropped you into 10% oxygen right now, you'd be gasping.
Oh, completely.
It would be like standing on the summit of Mount Everest without an oxygen tank.
Precisely. You wouldn't be able to think clearly. You'd barely be able to move. And yet, this is the exact time when the first complex animals evolved.
That seems like a massive paradox. How do you have an explosion of complex life in a suffocating atmosphere?
The report suggests that early animals were essentially adapted to high-altitude conditions in the ocean. They had to be incredibly efficient.
So they weren't moving fast.
No, they likely had very slow metabolisms. But as the Paleozoic progresses, we see this oxygen pulse.
It starts creeping up.
Slowly at first. By the Devonian, which is known as the age of fishes, we're up to maybe 15 or 20%. And do you notice the correlation there?
More oxygen, bigger animals.
Bigger and much more active. You cannot be a high-speed predator chasing down prey if you can't breathe. High oxygen supports high metabolism.
Makes perfect sense.
But the real spike happens later in the Carboniferous period.
The graph just goes completely vertical.
It shoots over 25%, maybe even 30 or 35%. We are talking about a hyperoxic world. The air was literally thick with oxygen.
And this links directly to one of the most famous facts about prehistoric life, right? The giant bugs.
Yes. This is the era of the dragonflies with the wingspans of a hawk.
Like Meganeura.
Exactly, Meganeura. A 2-foot wingspan. Or Arthropleura, which was a millipede basically the size of a car.
Okay, but why does oxygen make bugs big? Why doesn't it make me big? If I breathe 35% oxygen, I don't grow to be 10 feet tall.
Because of how insects breathe. It's totally different from us. They don't have lungs and blood that actively pump oxygen around the body like we do.
Okay.
They rely on a system of tracheal tubes, basically little pipes that open to the outside air. It's a passive diffusion system.
So the air just sort of floats into them.
Essentially, yes. In our modern atmosphere at 21% oxygen, that system becomes really inefficient if the insect gets too big. The oxygen just can't reach the deep tissues fast enough.
So a giant bug today would just suffocate inside its own body.
Exactly. But crank the ambient oxygen up to 30 or 35%.
And that limit is completely removed.
The ambient pressure pushes the oxygen deeper, faster. You can power a much larger body. The atmosphere literally dictated the maximum physical size of life.
So the atmosphere shaped the biology. That's incredible. But oxygen has a partner in this chemical dance, and that's carbon dioxide.
Yeah.
And looking at the CO2 numbers in this report, wow.
They are staggering. In the early Paleozoic, so the Cambrian and Ordovician CO2 levels were likely 10 to 20 times higher than pre-industrial levels.
10 to 20 times.
We're talking over 3,000, maybe even 4,000 parts per million.
Today we're panicking, and rightfully so, about hitting 420 or 430 ppm. 3,000 sounds like an absolute death sentence. Why wasn't the Earth boiling? Why weren't the oceans evaporating into space?
That brings us to something called the faint young sun paradox.
Okay, what is that?
It's a standard fact of stellar evolution. Stars get brighter and hotter as they get older. So back in the early Paleozoic, the sun was about 4 to 6% dimmer than it is today.
So the Earth was receiving significantly less heat from space.
Significantly less. If we had modern CO2 levels back then with that dim sun, the Earth would have been a snowball. It would have frozen solid. The Earth actually needed that massive greenhouse blanket just to keep water liquid.
It's a really delicate balance. A dimmer sun requires a thicker blanket.
Exactly. But then, as the era progresses, the blanket gets pulled away. Through the Devonian and Carboniferous, CO2 levels absolutely crash. They drop massively.
And the report lists a few culprits for this drawdown. But the main one is surprisingly humble.
It's plants.
Plants.
Specifically, the expansion of land plants. This is crucial. When plants colonized the land, they evolved roots. And those roots did something the Earth had never, ever seen before. They started eating the rocks.
Eating the rocks, come on.
Chemically, yes. We call it silicate weathering. Roots secrete acids to break down rock so they can extract nutrients. This process triggers a chemical reaction that literally pulls CO2 out of the atmosphere to form bicarbonate.
Okay, and where does that go?
It eventually washes into the rivers, goes into the ocean, and gets locked up as limestone on the seafloor.
So the trees literally ate the sky.
In a very real way, yes. The invention of roots acted like a planetary vacuum cleaner for carbon. And combined with the burial of organic carbon in coal swamps, which locks that carbon underground so it doesn't decay, the atmosphere was basically stripped of its CO2.
And since the sun was still relatively dim at this point, what happened to the global temperature?
It plummeted. This biological activity actually cooled the planet significantly, leading to massive ice ages that we'll talk about a bit later.
It's just amazing to think that biology, just simple plants growing, can alter the global climate so drastically.
It's the first time life really grabbed the wheel of the climate system. Life isn't just a passenger on Earth, it's a driver.
So we have the stage set, continents are crashing into each other, oxygen is rising, CO2 is falling. Let's talk about the actors on this stage. Moving to section 3, the biotic revolutions.
We really have to start with the Cambrian Explosion, 538.8 million years ago. The report calls it the evolutionary storm.
Right, because before this, life was what? Mostly just slime.
Mostly microbial mats, bacterial colonies, maybe some weird soft-bodied, quilted organisms called the Ediacaran biota. They were entirely passive. They just lay on the seafloor absorbing nutrients.
Sounds like a peaceful garden of blobs.
Exactly. And then, in a geologically super short window, maybe just 20 million years, we get the explosion. 35 plus new animal phyla suddenly ensure in the fossil record.
And phyla, just to clarify, those are the big categories, right? Like arthropods or mollusks or chordates.
Yes. These are the basic fundamental body plans, the blueprints. Almost every major animal group we have today started right here in the Cambrian. And the shift is profound. It's a shift from soft to hard.
We see shells for the first time.
We see shells, we see armor, we see teeth.
The report calls this an arms race.
That's the best way to describe it, honestly. Before this point, there was no predation, no one was eating anyone else, and then suddenly, nature invented the predator.
Enter Anomalocaris.
The world's first super predator. It looked completely alien. It had huge compound eyes on stalks, 2 grasping appendages in front that looked like shrimp tails, and a circular pineapple slice mouth full of teeth.
Wow.
It was the T-Rex of its day, just swimming through those shallow seas, picking things off.
And if there is a T-Rex, you need a bunker. You can't just be a soft blob anymore.
Exactly. The prey responded by biomineralizing.
Building shells.
Right. Extracting minerals from the water, like calcium carbonate, to build armor.
So basically, if there are no predators, you don't waste the energy building a heavy shell. But the second Anomalocaris shows up, you build a shell or you die. The invention of the skeleton was basically a military defense contract.
100%. It costs way too much metabolic energy to build a shell if you don't need it, but necessity drives evolution.
And we know all this because of sites like the Burgess Shale in Canada.
Yes, the Burgess Shale is incredibly famous because the preservation is so perfect that we can see the soft parts of the animals, not just the hard shells. We can see all the bizarre experiments that evolution was running.
The report calls it architectural experimentation.
It really was. Nature was trying out weird shapes, animals with 5 eyes, animals with vacuum hoses for mouths. Many of those designs just didn't survive the test of time.
So the Cambrian builds the blueprints. But the report distinguishes this from the next big event, the Great Ordovician Biodiversification Event, or the GOBE.
Right. Think of it this way. If the Cambrian was constructing the house, the GOBE was furnishing the rooms.
I like that.
The Cambrian gave us the phyla, the broad categories. The GOBE gave us the families, the genera, the species. Marine diversity completely tripled during this time.
And this is where the marine ecosystems start to look a bit more familiar to us.
Yes, you get the first really complex reefs built by rugose and tabulate corals. You get the plankton revolution,
which is microscopic organisms like acritarchs and zooplankton. It's exploding in numbers. Why does the plankton matter so much in the grand scheme?
because they are the ultimate base of the food chain. More plankton means way more energy for everything above them in the water column. It allowed for much more complex food webs. We also see cephalopods, the ancient ancestors of squid and octopuses, becoming the new apex predators.
They took the baton from Anomalocaris.
They did. They got bigger and smarter.
And what were the drivers for all this diversification?
It's that perfect storm again. High sea levels providing lots of warm, shallow shelf space, warm global climates, and oxygen crossing a critical threshold that allowed for these highly active, predatory lifestyles.
So the oceans are just teeming with life. It's a busy, dangerous, colorful place. But the land is still pretty much barren rock. Until we get to Section 4, the conquest of land.
This is arguably the most difficult transition life has ever made.
Really? Harder than evolving eyes or something.
I'd say so. Going from water, where you're supported by buoyancy and surrounded constantly by dissolved nutrients, to the air, where you have to support your own physical weight against gravity and somehow find water constantly so you don't dry out, it's a massive challenge.
And it started humbly, right? It wasn't overnight for us.
Very humbly. In the late Ordovician, you maybe have some simple mosses or liverworts just hugging the wet rocks right near streams. Nothing tall, but the real breakthrough comes in the Silurian with a tiny plant called Cooksonia.
Cooksonia. Sounds like a kitchen appliance, but describe it for us. What made it special?
It's tiny, maybe a few centimeters tall, just a simple green stalk that forks at the top, but it had an absolute superpower. Vascular tissue.
Internal plumbing.
Internal plumbing.
Yeah.
Xylem and phloem. It could actually transport water from the ground up to its cells.
Which allowed it to grow upwards.
Exactly. It could stand up just a little bit against the pull of gravity. It broke that absolute tether to the water's edge.
But by the Devonian period, we get the real explosion. The Devonian explosion of plants.
Yes. Plants evolved lignin.
Wood.
Right, wood. Lignin is a really tough, complex structural molecule. Now they could build strong, rigid trunks. We see Archaeopteryx, which is basically the first true tree. It had deep roots, it had branches, and it could grow tall, forming the very first forests on Earth.
And as we discussed earlier, those deep roots profoundly changed the planet's chemistry.
They broke the rocks, they drew down the CO2, and they cooled the Earth. The greening of the Earth literally terraformed the planet, making it cooler and way more oxygen-rich for the animals that would eventually follow them onto land.
Speaking of animals, meanwhile, back in the water, the Devonian is famous for something else. It's literally called the Age of Fishes.
It is, and specifically, it's the shift from jawless fish to jawed fish.
Wait, fish didn't always have jaws. I think we assume jaws are standard equipment.
No, the early fish, the agnatha, think of things like modern lampreys or hagfish, but covered in bone, they were basically armored vacuum cleaners.
Just sucking things up.
They just sucked up muck and algae from the bottom. They had absolutely no biting mechanism.
So how did they get a jaw? Did a bone just decide to move?
Well, evolution is a tinkerer, not an engineer. It almost always repurposes existing parts rather than building from scratch. Fish have gill arches, these bony supports that hold the gills open so water can flow over them. Evolution took the first pair of those structural arches and hinged them forward.
That is quite an upgrade. From a breathing tube to a weapon.
Initially, it was probably just to pump water over the gills more efficiently, like a ventilation pump so they could breathe better. But once you have a hinge that can snap shut, well, you can bite things.
And if you can bite, you can eat bigger, tougher prey.
And that leads to the monsters.
The placoderms, like Dunkleosteus.
Yes. Imagine a fish the size of a school bus, maybe 30 feet long, completely covered in biological tank armor.
And the teeth.
It actually didn't have teeth in the modern sense. It had exposed self-sharpening plates of solid skull bone that acted like industrial shears.
Terrifying.
It could bite with thousands of pounds of force. It could shear right through another armored fish like it was butter.
Okay, I'm glad they aren't around anymore. But amidst these massive armored monsters, there's a smaller lineage that's infinitely more important to us. The lobe-fin fish.
The Sarcopterygi. Yes, this is a crucial distinction to make. Most fish you know today, goldfish, bass, tuna, salmon, they are ray fin fish. Their fins are basically webs of skin supported by flimsy, delicate little spines.
Okay.
But lobe-fin fish, they have a meaty, bony, muscular stalk inside their fin.
A structure that looks suspiciously like an arm.
Exactly. One thick bone at the top, two bones below that, and lots of little bones at the end. The humerus radius ulna pattern, the exact skeletal structure of your arm, started right there in the fins of these Devonian fish.
Which brings us to section 5 of the report, from fins to feet, the tetrapod transition.
Now, we need to debunk a major myth here. You've seen the cartoon, right? A brave fish looks at the dry land, decides it wants to go for a walk to find food, and just crawls out of the water.
That is the classic image. It's on motivational posters everywhere. Evolution, take the next step.
And it is completely wrong. Evolution doesn't plan ahead. A fish doesn't know there is land to conquer. And a fish that flops onto land with fins doesn't evolve legs, it just dries out on the sand and dies. This was a 25 million year process of aquatic adaptation.
So they weren't building legs to walk on land at all.
No, they were building limbs to navigate shallow, weed-choked water.
Let's walk through the sequence the report lays out because it's fascinating.
It starts with tetrapodomorphs like Euthenopteron. It's very clearly a fish, but with that internal lobe structure in the fin really well defined. Then you get prototetrapods like Elginopeton. They have mosaic traits, a true mix of fish and amphibian features.
And then the absolute game changer, Acanthostega.
Acanthostega is the smoking gun of evolution. It lived about 360 million years ago. It had 4 defined limbs. It had digits 8 fingers on each hand, actually.
8 fingers, so it walked on land.
No, that's the twist. It had internal gills. Its hips were far too weak to support its own weight out of the water. It was a fully aquatic animal that just happened to have fingers.
So it used its hands to paddle.
Or to push through dense vegetation in the swamps. Think of it like 4-wheel drive for a swamp. It allows you to grab onto submerged roots and pull yourself through shallow water where a normal swimming fish would just get hopelessly stuck. It shows that limbs and fingers evolved in the water for use in the water long before they were ever used for walking on land.
That is a huge aha moment. We usually assume legs equal land, but legs were just better fins for a specific underwater environment.
Exactly. This is a concept called exaptation, using an existing biological trait for a totally new purpose later on. The legs were there for swimming and navigating swamps. Millions of years later, they turned out to be really useful for walking.
Now, the report mentions a specific mechanism for this kind of morphological change called heterochrony. Can we translate that into plain English?
Sure, it sounds complex, but it basically means changing the timing of development. Evolution creates new shapes by speeding up or slowing down the growth rate of different body parts during an animal's life.
Okay, and one specific type mentioned in the report is paedomorphosis.
Right, which simply means retaining juvenile traits into adulthood.
Give me an analogy for how that works.
Well, look at our friend Acanthostega. Its skull proportions look incredibly similar to the juvenile skull of its fish ancestors.
Okay.
Baby fish often have shorter snouts and proportionally larger eyes. By freezing development at that juvenile stage, but letting the animal grow to full adult size, evolution can create a totally new head shape, one that might be structurally stronger for biting without having to reinvent the genetic wheel.
So nature is basically hacking its own code. It's using the existing blueprint of a baby fish to build the skull of an adult tetrapod.
Exactly. It's an incredibly efficient way to innovate.
So we have animals that can survive in the shallows. We have plants turning into towering trees. Now we move into the late Paleozoic, and the world is looking very different.
This is the Carboniferous period. And if you have a mental image of a prehistoric jungle, this is it. The coal forests.
Giant trees.
Actually, they weren't true trees in the modern sense. They were giant club mosses called lycopsids and giant horsetails. Imagine a moss that grows 100 feet tall, or a horsetail reed the size of a telephone pole.
That's surreal. And this is where the atmosphere goes wild again, right?
High oxygen over 25% and very low CO2. We already discussed the giant insects that this allowed, but the true legacy of this era is in the ground. These forests grew in vast, waterlogged tropical swamps. When the plants died, they fell into the water.
And usually wood rots.
Right. Fungi and bacteria eat it, break it down, and release the CO2 back into the air. But in the Carboniferous, two unique things happened. One, the swamp water was acidic and very low in oxygen, which severely slows down decay.
And two,
Plants had just evolved lignin, that tough wood fiber we talked about. It's highly probable that decomposers, like bacteria and fungi, simply hadn't evolved the specific enzymes to digest lignin efficiently yet.
so the trees were essentially indigestible?
They were junk food that no one could eat, so they didn't rot. They just piled up, layer upon layer of peat. Eventually, heat and pressure turned that massive amount of peat into coal. These are the coal swamps. The rate of burial was so fast, it sequestered massive amounts of carbon out of the active carbon cycle.
Which brings us back to the climate.
Ugh.
If you bury all the carbon in the ground, the greenhouse blanket gets very thin.
And the Earth freezes. This is the late Paleozoic Ice Age. It's deeply ironic. The incredible explosion of terrestrial life, the forest, actually drove the planet into a deep freeze.
Now, the report talks about tectonic phases here. It wasn't just one unbroken block of ice, right?
No, it wasn't a solid block of Ice Age. There were rhythms. Phase 2, roughly 330 to 280 million years ago, was a time of relative tectonic calm. Volcanic activity was low. Because of that calm, the climate became exquisitely sensitive to Milankovitch cycles.
Remind us what those are.
Milankovitch cycles are natural, predictable wobbles in Earth's orbit and tilt. They change how sunlight hits the Earth.
So you had rhythmic sea level rising and falling as ice caps grew and melted.
Exactly. And that rhythm is what buried the coal in such distinct layers. Swamp forms, makes coal. Sea level rises, floods the swamp, leaves mud. Sea level drops, swamp returns, makes coal. Swamp mud, swamp mud. It's why coal seams are layered today. It's basically a barcode of ancient climate cycles.
But all things must pass. The icehouse world begins to fade as we enter the Permian period.
Tectonics wakes up again. Pangea is fully assembling now. We have one massive north-south supercontinent, and the climate radically shifts from icehouse moist and cold to greenhouse, arid, dry, and hot.
The swamps dry up.
They do. The interior of Pangea becomes a harsh desert, and this sudden change in environment completely forces a change in the dominant animals. Amphibians, like our friend Acanthostega's descendants, they are fundamentally tied to the water. They lay soft, jelly-like eggs that have to stay wet.
Which is very bad news in a desert.
Terrible news. You dry out and die. Enter the amniotes. They evolve the amniotic egg.
The portable pond.
That is the perfect description. It has a hard or leathery shell that keeps moisture locked in. Inside, the embryo floats in its own private fluid sac. This evolutionary leap allowed animals to finally cut the tie with the water completely.
They could march right into the arid interior of Pangea.
And two major groups diverge right here, the sauropsids and the synapsids.
The sauropsids are the reptile and eventually dinosaur ancestors. But the synapsids,
Those are our ancestors. the mammal line. And here's the plot twist that most people don't know. In the Permian, they were the rulers.
We usually think reptiles ruled first, then mammals scurried around in the dark, and then mammals took over after the dinosaurs died.
That's the standard pop culture narrative. But before the dinosaurs even existed, the synapsids were on top. Large, sail-backed animals like Dimetrodon. They were the dominant land animals. They were incredibly diverse. They were large, and they were everywhere.
It looked like a planet of proto-mammals.
It absolutely was. But their reign was about to be cut violently short by the greatest catastrophe the world has ever seen. Section 7. The Great Dying.
The end Permian extinction. 252 million years ago. The stats in the report are just terrifying.
They are hard to even comprehend mentally. 96% of marine species, gone. 70% of terrestrial vertebrate species, gone. It is the only mass extinction in Earth's history to hit insects significantly.
Usually bugs survive everything. Cockroaches, right? They're the ultimate survivors.
Even the cockroaches took a hit here. Entire orders of insects were wiped off the map.
So who is the culprit? The report points the finger directly at the Siberian traps.
Yes. And traps here comes from a Swedish word for stairs, referring to the stepped, layered look of the basalt rock that was left behind. This wasn't a normal volcano. This wasn't Mount St. Helens blowing its top. It was a flood basalt event.
How big are we talking?
1.5 million cubic kilometers of lava. That is enough lava to cover the entire contiguous United States in a layer of molten rock hundreds of meters thick.
But the lava itself didn't kill the whole world, right? I mean, it didn't physically flow to South America or Africa?
No. The lava was local to Siberia. The gas was global. The magma plume happened to punch upward through a massive underground basin of coal and evaporates, basically salt deposits.
Talk about incredibly bad luck.
The worst luck possible. It was like drilling directly into a fossil fuel refinery and setting it on fire. It injected massive, unprecedented amounts of sulfur dioxide and carbon dioxide directly into the atmosphere.
The CO2 spike was instant.
Geologically speaking, yes. Over a few thousand years, it jumped from around 400 parts per million to 2,500 ppm.
And the global temperature
rose by about 8 degrees Celsius. That's 14 degrees Fahrenheit. That is a global fever that breaks the whole system.
So I have the trigger. What were the actual kill mechanisms? How did the animals actually die?
It was a multi-pronged attack, like a firing squad. First, hyperthermia. It simply got too hot for physical life, especially in the tropics. At a certain temperature, proteins in your body literally start to denature. You cook.
Brutal. Second,
ocean anoxia. Warm water fundamentally holds less dissolved oxygen than cold water. Combine that with high metabolic demand from the extreme heat because animals need more oxygen when it's hot, and the ocean circulation slowed down to a halt. The oceans essentially suffocated. 80% of the oxygen in the ocean was lost. It became a stagnant, toxic dead zone.
and acidification.
Right. All that massive CO2 absorbed by the ocean turns into carbonic acid. It collapses the carbonate cycles. Organisms that build shells, corals, mollusks, microscopic plankton, they couldn't build their skeletons. The water was so acidic they dissolved.
And the report mentions one more nastiness, ozone depletion.
The halogens released by the burning salt deposits in Siberia destroyed the ozone layer. So on top of the suffocating heat and the acid oceans, you have intense, sterilizing UV radiation blasting the surface of the Earth, causing massive mutations in surviving plants and pollen.
It really was hell on Earth.
It was. The aftermath describes a coal gap in the geological record. We completely stopped seeing coal for millions of years because the forests were simply wiped out. There was nothing left to make coal. And then there's the fungal spike.
The fungal spike.
Hmm.
That sounds like a horror movie title.
It basically is a horror movie. In the sediment layers, right at the extinction boundary, pollen from trees and plants almost completely disappears. Instead, we see a massive global surge in fungal spores.
Why fungi?
Because fungi eat dead stuff, and the whole world was dead stuff. The cleanup crew took over the planet.
How long did it take for the Earth to recover from this?
Painfully slow. It took 30 million years for vertebrate fauna to recover its numbers and diversity. 30 million years of mostly empty, struggling ecosystems.
That is a sobering number.
It is. We lost entire lineages that had been incredibly successful. Trilobites, which had survived for nearly 300 million years, vanished. Eurypterids, the sea scorpions, ancient corals, they were gone forever.
So as we wrap up this deep dive, let's synthesize what we've learned from this massive report. We started with the breakup of Pannotia, and we ended with the assembly of Pangea.
A full tectonic cycle. But the biggest takeaway for me is the coevolution. Life didn't just live on the rock passively. It profoundly changed the rock. Plants altered the weathering patterns and cooled the climate. Life changed the air, pumping it full of oxygen and sucking out the CO2. The Earth and its life are inextricably linked.
And the modern parallel, because the report leans into this.
It's impossible to ignore. The end Permian mechanisms, rapid injection of CO2 into the atmosphere, global warming, ocean deoxygenation, ocean acidification, those are the exact same phenomena we are observing today.
We are seeing the early stages of the Great Dying mechanism.
Exactly. The Great Dying serves as a stark warning. It shows us exactly what happens when geochemical thresholds are breached. The system doesn't just adjust gradually, it can collapse catastrophically.
And that leads to a final provocative thought from the report.
Right. The recovery took 30 million years. If we view the Paleozoic as a cycle of building complex ecosystems, spending hundreds of millions of years constructing a biological masterpiece, and then burning it all down in a geological instant, we have to ask ourselves a very hard question. Are we currently acting as Siberian traps of the modern era? We are digging up the carbon, we are releasing it, we are acidifying the oceans.
We are the volcano.
We might be, but unlike a blind volcano, we actually have a choice. We can see the pattern in the rocks. We can change course.
That is definitely something to think about. This has been a heavy but incredibly important deep dive into our planet's biography. Thank you for listening.
Keep asking questions.
See you next time.